Now we will discuss this example about drawing, how to draw or how to use a flammability chart to determine where the area or the flammability zone in that area. You will need some information about the lower flammability limit and the upper flammability limit of a specific material in pure air and in pure oxygen as well. And you will need to know how to draw the stoichiometric line, we need to know how to draw the LOC, how to determine the region of the flammability zone, and then we're gonna decide which zone will be the flammability zone. And now we're gonna do this exercise together, although I have done it in the previous few slides, but let's do it together now, and let's see step by step how do we do it. In the question I have what we call the product or the component is the methane. And I need to specify where is the flammability zone or where is the flammability region for the methane. So I have some piece of information that I will require or I will need. I have the lower flammability limit is 5.3 of fuel in air, and I have the upper flammability limit to be 15% of fuel in air. So you have to keep in mind that these are the values in air, not in pure oxygen. And they have the value as well in pure oxygen, where the lower flammability limit is equal to 5.1 of fuel in oxygen here, not in air. And they have the upper flammability limit to be 61 of fuel in oxygen as well. I know that LOC equal to 12%, or I have been given this piece of information. Now we're gonna establish, and if you still remember, I'm gonna draw just quick sketch. I'm gonna draw the triangle, nitrogen, fuel, which is methane, M, and here oxygen. If you still remember, we need few lines. We need to draw three lines. The first line is the air line, and we said that this is fixed. The second one is the stoichiometric line, and the third one is the LOC line. Okay, so we need to establish 3 lines from that. Now for the air lines, we know that it normally goes from this point to this point, where you have 79% nitrogen, 21% oxygen. So by default, we will know how to draw the air line. Now let's look at the stoichiometric line. The stoichiometric line, we said that it goes from this point where I have 100% of nitrogen to a point in the oxygen concentration. And I need to determine this point, and in order to determine this point, I'm going to use this formula, which is Z divided by 1 plus Z multiplied by 100%. And if I am talking about methane, then when I oxidize methane, I will get CO2 and H2O, I will get Z equal to 2. Therefore, I can replace this Z here to be equal to, and I get the percentage of oxygen to be equal. So this point will represent a concentration of oxygen which is equal to 66.7 or 67, you can say, approximately. Okay, so I know that by default that this point has to read 66.7. So now we're gonna see how we're gonna place these pieces of information, and how we're gonna establish it on the flammability chart. Okay, so now let's go. Let's start step by step. So as we mentioned, we're gonna draw first the air lines. I'm gonna draw the air lines in red, and we said that it goes from the point where you have 100% fuel and no air to the point where you have 79% nitrogen and 21% oxygen. So now we have already drawn the air line. Now we're going to look at the stoichiometric line, and we calculated, or we found where is the location for this point, which is 66.7. So we're going to draw this line as well. Okay, so now we have another few pieces of information. The first piece of information that we have is the LOC. The LOC is 12% of oxygen. So I know by default that it will start here, but I will know where it touch by drawing the other point. So now we have the upper flammability limit and the lower flammability limit in oxygen, and the upper flammability limit and the lower flammability limit in the air as well. So if I'm talking about oxygen, this means that I'm looking at this point. I'm going to draw it now in green. So once I refer to the upper flammability limit and the lower flammability limit of methane in oxygen, this means that it has to be at this point or at this line. Okay, so it has to be somewhere at this line or located somewhere at this line. and I know that the upper flammability limit for methane in oxygen equal to 61%, means that I have only methane and oxygen and I have no nitrogen. So it has to be located at this line, the green line, which is the oxygen line. So it has to be here, where it can reach 61% of methane and 39% of fuel. So this is the first point that I'm gonna read. Okay? Then I know that the lower flammability limit for methane in oxygen as well is 5.1, which means that this combination has only methane and oxygen, which is this point. So now we learn, or we know, where is the large border or the maximum border for the upper and the lower flammability limit. And now I'm going to use the other two pieces of information, which is the upper flammability limit and the lower flammability limit in air, for methane in air, to determine the region. So if I'm talking about lower flammability limit and upper flammability limit of fuel or methane in air, this means that I'm looking at any point or any combination, since it's in air, inside the triangle. But I know by default that the concentration, or the upper flammability limit and the lower flammability limit is the concentration of a fuel in air. So I can simply say that if the lower flammability limit is 5.3, if the lower flammability limit of methane in air is 5.3, this means that the point at 5.3% of fuel in air will give me any line, أي line عليها حيكون to represent, or will represent to me, what we call the lower flammability limit. And I go and do the same thing for the upper flammability limit, which represents 15% of methane in air, which means that at 15% of fuel I can draw another horizontal line, and now I have established the border. Now I'm gonna establish the zone or the area. So I have the upper flammability limit has to be connected to the upper flammability limit in oxygen, and the lower flammability limit of oxygen has to be connected to the lower flammability limit in air. Okay, and now we're gonna establish somehow a point where it touch barely, that's why where the approximation come, and it touch barely the flammability zone. So if I know that the LOC line will be at this point, so approximately the LOC will be this way, and if it barely touch the point, this means that it has to be this way. And as a result, I'm going to draw it now in let's say in red. If any, as a result, any point in this region, or if I take any concentration in this region, this will be flammable zone, or the fire will start if I have the combination or the concentration of oxygen, nitrogen and fuel at any point here, for example, here, here, here. Any point at these zones, the fire will start. Any point above or below this zone or out of this zone, the fire will not start. So I hope it's clear, the demonstration. We're going to see in the next two slides how they establish it in more details, but I have already explained how to establish. So now this is another, this is the final chart that you will get for methane. But as I mentioned earlier, the chart, if you and I'm going to show it on the next slide, the chart, for example, for other chemical will be completely different, but it has the same principle, where the line, the area dotted in red is the flammability zone, and the area, let me put it this way. So this whole area, by the way, not this whole area, is flammability zone. Okay? So anything here is a flammability zone. Anything here is non-flammable, or here. This is non-flammable zone, and the red one is the flammable zone. This is another slide. This is another example for ethylene, and if you can see, because ethylene has larger or wider flammability zone, you can see that the area or the shape of the area completely change, and the area become really larger than the classical methane example that we have seen before. So this is the whole area of flammable zone. So this is for ethylene, and as I mentioned, if you use H2 you will get completely different slide, you will get completely different shape. But you have to keep in mind that if you flip the elements, if you change for example nitrogen with oxygen, oxygen with ethylene, you will get completely different shape. You have to keep in mind that this is based on the fact that you are using the nitrogen as the horizontal line, and the two other elements is the fuel and the oxygen as well in that specific organization.